right? So the black ones, we are told that is Asha. Okay, I hope I'm telling correct. So this is basically A, and the other one is, I'm gonna call the S. So this is A, this is S, and this is like A, and this is Sasha, and this is A and S, and stuff like that. So you don't have to write it, but it's good to know which one is which. So we are told we are actually finding the average of how many more minutes per day did Sasha study than Asha, okay? So we may find the difference between each day and then kind of take the average from there, or we can just add the total number of study by each person and then see the difference, and we can take the average after, which is also fine. But I'll take the difference first. You know, the difference between these two, since we are looking for Sasha, right, which is the S. So on the first day, Monday, Sasha did like this is 60, this is 80. So you have right in the middle 70. This is 70, this is 60. There is a difference of 10. So the Sasha did 10 more on the first day. I'm gonna say this is a plus 10. The average is what we are looking. So, and then choices are lesser than or equal to 12. So 130 looks too big. And the second one, the A did more than the S. So this is 90, this is 80. So that is 90, this is 80. So this S, which is the Sasha, actually have 10 lesser than the A, okay? And the next day, this was 100, this is 120. So what we care about Sasha, which is a plus 20, the difference between those two. And the next one, this is 80, this is like 110. So there is a difference of 30, and then Sasha has more. And the last one, this is 70, and this is 50, the difference of 20, but Sasha did less, so which is why it's gonna be minus 20. So again, if you are asking why this is minus, plus, and stuff, I'm just taking the S and comparing with the A and D. So we want A and C to be opposite, right? So A and C has to be opposite. So as you see, this is one way to do this. But since we have circle, we need to be careful because we may rotate it to get the same, like same setting. So meaning that if I, let me draw another one. So if I do another circle, so let's say this is A, this is B, this is C, and this is D. This guy and this guy is actually the same because A and C is opposite, B and D is opposite. It was the same case, but even though the A is right now in the to the right of the circle, which doesn't matter because we have the same like ordering. So which is why when we are trying to arrange the things on a circle, we like to be careful, okay? So the rotation will make a bit different. So that if this is the same, then let's not get the same. So if A is right here, okay, so the C is right here. So if I do the other way around, let's say this is B and this is D. But this is also same as this one. So it just goes this way, you know, A, B, C, D, right? So if you go this way, that will be A, B, C, D, and then you can rotate this way all the way to the here. So A could be getting here, and then B will be here, so same as this one. So which means this guy and this guy is also same arrangement. So there is no difference. So the probability that we are looking for is the desired outcome over total cases, right? But how many ways can we have A and C are opposite? So we could have A, B, C, D. So if I just go, actually this is different, right? So if I move this way, A will be here. So let's try to see if this is the same. If I move 90 degrees to the like counterclockwise, so that will be A, and then this B will be here, and then this C will be here, and then D will be here. But this is actually different from this guy. So A is right here, C is right here, but B and D change. So meaning that we do have two different arrangements. So not just one. So there are two basically desired outcome, which is like this one and this one. But the question is, how many total outcome do we have? So this is the two. If you want to go ahead and list them, you may actually find a number of ways because it's not too many. So you can just say, okay, A is right here, maybe C is next to A, so you can go with A, C, B, D. And then if A and C is next to each other, so you will probably get two arrangement like that. And then if you have maybe A and like B on the other side, so you can get another arrangement, but you can kind of list them. But there is a shortcut that we use for the arrangement on a circle. So if you have n people, okay, we can do n minus 1 factorial ways arrangement to arrange on a circle. So since we have 4 people, okay, so the total outcome should be 4 minus 1 factorial, which is 3 factorial. And then 3 factorial is just 3 times 2 times 1, which is 6. So total outcome in our case is 6. So 2 out of 6 will be the answer, which is the part choice B. So again, if you have a circle, the number of ways to arrange this would be n minus 1 factorial. So if you are asking why this is the case, because if you have this A right here, and then B is seated like that, you can always arrange it. Like you can get this A right here, B right here, C right here, D right here. So you can rotate it to get the same picture. So regardless of how you start, you can always rotate it, and then you can just get exactly what you are trying to get. So that is why for the first guy, doesn't really matter. So you just need to place the other people around that first guy. So which is why you have one lesser number of people that you really need to actually place around the circle, which is why we say n minus 1 factorial. Okay, so that is just a like one approach to say why that is n minus 1, but that is the case. So we have two congruent squares, right? A, B, C, D, and P, Q, R, S. So that is important, and the sides are 15. So let's write that. So this is 15, and this is 15. So like it's good to write these. So these are 15, and this is also 15. A to B and S to R, or D to S and stuff, D to C actually. And then the overlap the region is 15 by 25. Rectangular view. Okay, so how this is possible? You know, this is 15, which means this is also 15, but they overlap to form a 15 by 25 rectangle AQRD. So AQRD. Okay, which is good. That means A to Q is 25. If that's 25, so since this is 15, so that should be 10. And the same reasoning, SR is 15, DS should be 10. So the SC has to be 5 because the DS was 15. And then PS is the same as AD, which is also 15. So the area of this region is what we need because we need to find the percentage of the whole piece compared to shaded region. So the shaded region is divided by the total, right? That is the percentage that we are looking. Shaded region is 15 times 5. And the total region is 15 times 25. So you don't really need to multiply when you have some simplification. So that will be 5 over 25. You may multiply by 4. So that will be 20 over 100, which is just 20%. And we are done. Okay, so we are given some ratio, like boys to girls is 5 to 4 in the first school. So at the end of the day, we are looking for the fractional part of the girls, right? So which is why I like to know how many girls on each school, so I can use that to find my ratio. So the ratio of boys to girls is 5 to 4, meaning that for every 5 boys, there are 4 girls in that setting. So which means 4 out of 9 students are actual girls. So if that's the case for the first school, 4/9 of the total number of students has to be girl. So 4/9 of 270 is 4/9 times 270. And I can cancel these guys. So that should be 30 times 4, which is 12, but there is like 0, which is 120. So in the first school, we have 120 girls, right? So that is something. In the second school, the number of boys to girls is 4 to 5, and then the girls is the second number, which is 5 out of total of 9. So that is 5/9 of the total number of students in the second school is like girl, so which is 180. So if you multiply, these will cancel. You got 20 times 5, which is 100. So 100 girls in the second school. So again, if that doesn't make sense, you can take it a bit longer. So you can say 5 parts will be boys, 4 parts will be girls, total of 9 parts. And then you can divide this by 9, which will be 30, which means each part will be 30. And then you can multiply by 4 to get 120, and you can do the same thing with the second part. But I think using the fraction is way better because you don't have to do the longer way, okay? So 100 girls in the second school and 120 on the first school. What fraction of the students at the dance are basically girls? So the total number of girls is like 120 plus 100 divided by the total number, so 270 plus 180. If you add them, so you got 220. And then 270 plus 100, that's 370. 70 plus 80 is 150, which means another, that will be 450. So I can cancel these easily. 21 is only divisible by 2 and 11, so, but 45 is not divisible by any of these. So I think we are gonna leave as it is, okay? So that's the answer. So it's not too challenging, to be honest, even though this is slightly challenging looking, but that's the answer, okay? Let me see. It's not too challenging. It's, you may go ahead and multiply if you want to, which is not gonna take too long. But our goal is not really doing that tedious multiplication, because if you increase the power, like let's say 4 to the 20th power and 5 to the, I don't know, maybe 40th power, you don't really want to go through that multiplication. So that's not fun looking. So instead, we like to say something else, okay? And then if I ask you like maybe 10 square, like how many digits this number would be, you will just say this is equal to 100, which is just 3 digits, right? And if I ask you what would be 10 to the 4th power, so you will get 1 and 4 zeros after, so that should be 10,000, which basically 5 digits. So then if your number is a multiple, like power of, like, or multiple of 10, then you actually can easily count number of digits without really writing that number. So if you look at the next number, maybe 10 to the 25th, the meaning of this, you multiply 25 tenths. When you multiply 25 tenths, you will get 1 and 25 zeros after, which means 25 0 plus 1 is just 26 digits in total. So that would be just 26 digits. So as you see, if the number can be written as power of 10 or a multiple of 10, then you actually can easily figure out the number of digits without really finding the number itself. So that is the goal. So if you look at the number like 4 and 5, it's actually easier to do that as well, because 4 can be written as 2 squared, and then you get 5th power of that times 5 to the 10th power. And if you remember one of the exponent properties, like whenever you have a to the x power and to the some other power to this, so we call this is power on power rule or power rule. You multiply this power by this power, so that means a to the x times b. I just choose axb, but it doesn't have to be like that. So this is called power rule. So we have 2 to the second power to the fifth power. If you don't remember, you know, you can multiply 2 by 5, which is 2 to the 10. But if you don't, you can just write 2 to the second power 5 times. So you can just do 2 squared, 2 squared, 2 squared, 2 squared, 2 squared. So meaning that you have 2 twos, 2 twos, 2 twos, 2 twos, 2 twos. In total, when you expand those, there will be 10 of these twos. If you have 10 twos that you multiply, that is actually 2 to the 10th power. But we don't want to go with that. So we just need to say this is second power, this is fifth power and power. We just multiply those, which is 2 to the 10th power times and 5 to the 10th power. So whenever you have now the exponent, when they have the same power, which is 10 in this case, you actually can multiply the bases, which is 2 times 5 and then to the 10th power. So that will be 10 to the 10th power. And this is nice because that is similar to what we had. So whenever you have power of 10, you can actually add one more digit because 10 to the 10th power means 1 and 10 zeros after. So if you have, that means 11 triangles. Like we are given two sides, like 25, which is like nice because that's gonna give us a isosceles triangle. So let's go ahead and draw that. And the other side will be 30. So it doesn't have to be accurate, but I'm gonna make at least something that's similar. So let's say this is 25 and this is 25 and this is 30. And the other one is also similar to that one, but the third side is not 30 anymore. Okay, so that is like 25 and that is 25 and this is 40. And the question is asking find the relation between its areas. Okay, so in order for us to get the area of a triangle, we need to find, like there are a couple of ways, but the most basic ones, let me just write, is the base length times height, and then divide this product by 2. And if you are wondering why this is the case, like we can actually make every triangle by adding some additional pieces to make a rectangle. And then you are gonna see area of the triangle is gonna be half of the rectangle. And then rectangle is you multiply 2 sides. And if you have the half, that will be just 1/2. That's why we have 1/2 it here. But the proof, and that is kind of reasonable if you kind of go with that. But let's not try to explain why that's the case, but that's how we find it, okay? So to do that, we need to know the base, we need to know the height. In this case, you have 3 sides, you can use any side as your base, but I like to use the 30 as my base. The reason why that's the good, because when you drop the altitude from the top to that base, since this side is same as this one, that altitude, that height, will split the base into 2 equal pieces. So that should be 15, and that should be 15, which is nice. And after this point, there are a couple things we can do. We can use the Pythagorean, which is, I have to probably remind as well. So whenever you have a right triangle, okay, let me try this. So if you have a right triangle, so let's say this is A, and this is B, and this is C. This is 90 degrees, the opposite leg I'm gonna call C, and the other, opposite side is C, and then 2 sides that is next to 90 is I'm gonna call A and B. So by Pythagorean, when you square the legs, that is the side that is next to the 90 degrees. When you square those 2 sides and add it, that will be equal to square of the hypotenuse. And this is called Pythagorean theorem, okay? So that is good to know if you don't remember. Pythagorean theorem, right? And you may use this for any right triangle. If you know 2 sides, then you can find the third one. So let's apply this, because I know I'm gonna call this is H1. So the H1 to the second power, because this is one side in this triangle, that is next to 90 degrees, and the other side is 15, so that will be 15 square equals the square of the hypotenuse, which is 25 square. And your goal is to get this H1 alone. So if you square this, that's 225. If you square this, you got 625. And if you subtract 225 from 625, H1 squared will be 400. And then 400 is actually 20 squared, so that means H1 has to be 20. So that is the height of this triangle. So again, I square this one, 225, square 625. To get H1 alone, I subtract 225 from both sides. That would be 400. So take the square root, so we can get 20, or 20 squared is 400, so that H1 is 20. Okay, so far, this is what we have. I think B is not correct, so we'll see that. So that is 20, but we need the area. Area was, I'm gonna call A. Area is base, which is 30 in our case, times height is 20, divided by 2. And if you divide 20 by 2, that's 10. 30 times 10 is 300. Okay, let's keep this in mind. And this is what we can do to find the height. We can use the Pythagorean to find the height. But if you do know something we call Pythagorean triple, you don't have to do this piece. You can actually look at the numbers, like 25, 15. That's 5 times 5. This is 5 times 3. So we can say this is gonna be 4 times 3. I mean 4 times 5, which is 20, because there is a 3 numbers, which is we call Pythagorean triple, the most common Pythagorean triple. So if you have 2 of these 3 numbers in a right triangle, or any multiple of these, the third has to be there as well. But again, this is we can use, this is 5 times of this, and then this one is 5 times 3, so the other one should be 4 times 5, which is 20. Again, if you don't want to do this, if you see the Pythagorean triple, so you can use as well. But this is one of the Pythagorean triples. So if you don't know, just ignore this approach. But another triple that we have is 5, 12, 13. And then we have a few others like 8, 15, 17. And then we got a few more that we actually use a lot. But if you never seen this, just ignore for now. But any 3 numbers that satisfy the Pythagorean is called Pythagorean triple. If they are integers like this, that is really useful, okay? So anyway, let's move on to the second triangle. And I do the same thing, like if I drop the altitude from the top to bottom, so that would be 90 degrees. Since this is isosceles also, that should divide the base into 2 pieces. And I'm gonna use the Pythagorean triple in this case, instead of Pythagorean theorem. So if you say H2 squared plus 20 squared equals 25 squared, you actually can get just find the area of those 2 triangles. And I use the Pythagorean and Pythagorean triple to find the height. But there is something which I will mention, but I'm not gonna kind of go ahead and use it. There is something called Heron's formula. Heron's formula is also telling us the area of a triangle, actually any triangle, if you know 3 sides. Maybe it's good to try as well. Actually do that. So the second approach, without really using Pythagorean, whenever you have 3 sides, that is good to use the Heron's formula. Let me write that, how that looks like. So you may use the Heron's formula if you want to find the area of a triangle, and if you know the 3 sides. Okay, how this is gonna look like? So you have a random triangle. So let me kind of draw an example. So let's say this is A, this is B, and this is C. The formula looks like this. The area is equal to S times S minus A. A is one side. S minus B, B is the other side, times S minus C. And if you are wondering what is S, and then when you multiply all these numbers, and you're taking the square root of that product, and then the S is just the average of those three sides. A plus B plus C divided by 2. So if you take the average of this sum, if you take the half of that sum, okay, I said average, but it's not average because three numbers. If you take the half of the sum, so you get the S, and then if you multiply S by S minus A, S minus B, S minus C, and take the square root, that will be area. So let's see how this is gonna look like. For the first one, I'm gonna call A. But to do so, I need to find the S. So let's find the S. The S is, I'm gonna use S1. The 25, 25, and 30 divided by 2. That's 50 plus 30, which is 80, divided by 2 is 40. So that means the half of the sum of those three sides is 40. So I will start with 40 times 40 minus 25. So 40 minus 25 times 40 minus 25, because the other side is also 25, and then 40 minus 30. And when you multiply these and take the square root, we got what we want. So let's simplify a bit. You know, this is like 40. I can leave it. That's 15. This is also 15. So if you multiply 15 by 15, so I can write 15 squared, and then this is gonna be 10. So since we have a square root, it's good to have some perfect squares inside. And then this is 15 squared is already perfect square. If you multiply 10 by 40, that's 400. 400 is 20 squared. And if you take the square root of 400, that will be just 20. And then square root of 15 squared will be 15. So, and then there is no square root anymore. So that is gonna be 300. If you remember, this was the answer for the A. And if I want to use the same thing for B, let's see how this is going to look like. So the B will be, if you add 25, 25, that's 50 plus this 90, the half will be 45. So the S is 45, which is kind of similar to this kind. You add them and divide by 2, the sum. And then 45 minus 25 will be 20. 45 minus 25 is also another 20. 45 minus 40 is 5. Okay, and I can see that 20 squared will be here, so I can pull that as 20. And 45 times 5, if you multiply those, that's 225. But 225 is 15 squared, so I can pull that as 15. If you multiply by 20, that is 300. So if you are struggling how to deal with the radicals when you have some numbers like that, taking the outside, that means you are gonna work on radicals a bit, okay, just to get better. But this is how we can use the Heron's formula. Again, this is something you can use if you do know three sides, and if you like to find the area. That is one of the approaches. So we didn't use this as our first shot because since the triangle were isosceles, when you drop the altitude, so that was easier to deal with, okay? So that's why we don't have to use the Heron's always. Yeah, you don't have to use the Heron's always, but it's good to know as well. But that was the second approach. Whenever you are trying to write any number as power of primes, like we call prime factorization. Okay, so, and then there are like a couple approaches like to find the prime factorization of any number. Some people use like factor tree, but I don't really like it because it's long and then you don't need it. As long as you are good with dividing some divisibility like rules, it's good to use like just the divisibility. So when you look at the number you are given, 588, okay, so the last two digits is 88. So if the last two digits is divisible by 4, the whole number is also divisible by 4. So which is why I can divide this by 4 to make it a bit smaller. If I add the digit like 885, which is 16 plus 5, which is 21, that means this number is a multiple of 20. The sum of the digit is multiple of 3. When you have a number, the sum of the digit is multiple of 3 or 9. That is multiple of 3 or 9. So in this case, this number is divisible by 3 as well. So without really dividing, we can see It is divisible by 4, it is divisible by 4, like 3. So I'm going to divide by 4 first. If I divide 5 by 4, that 4 goes into 5 one time. And then that will be 1 remainder. So that will be 1 and 8. So 18. So 4 goes into 18 4 times. That's going to be 16. And then there will be 2 left over. So 28 7 times. And I do know this was divisible by 3, but it looks like this is way better to see it's divisible by 7. So I can maybe divide by either 3 or 7. But I will try with 7. So 4 is 2 squared. Okay, so that is something. And we have 2 squared, but if you divide this by 7, that will be 2 times. That will be 2 and 1, 21. 21 is 7 times 3, so that means this is going to be equal to this. So let's rewrite this. So you got 2 squared, and then we have 1 3, and then 2 7s, and then there is nothing else. So if that's the case, we are told 2 to the w power. So 2 has power of 2, which means w is 2. And then 3 to the x, 3 to the first power. So that means x is 1. And then 5 to the y. But there is no 5, which means 5. I can write 5 to the 0th power because 5 to the 0th power is just 1. So that means y is 0. And then the last one is z. 7 to the second power, which is 2. Okay, so then 2w is 4, 3x is 3, 5y is 0, 7z is 14. If you add 14 by this 18 plus this 21, and that is the answer. Okay. So prime factorization will be important. So this was just the prime factorization. Die, you are rolling that twice. Okay. And then when you roll a die, you have 6 possible like outcome that you can say 1 through 6. But if you roll 2 die, right? Then you will get every number could be paired with the another one, which means 1 could be paired with 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. So you have 6 different outcome. If your first die shows 1, the second die could be any of these 6 numbers. Or if the first one is 2, the second could be any of those 6 numbers. So if you just keep adding those 6s, that will be 36 total outcome. Or total outcome basically, you have 6 choices for the first one, 6 choices for the second. So if you multiply, you got 36 outcomes. This is the total outcome. Okay. And what you want is the first number is going to be larger or equal to the second number. So if the first number, let me just write kind of list, the first and the second. If there is not too many, it's okay to list. So if the first one is 1, right, the second one could be 1. That's the only case you can have. They are equal. If the second one is 2, the first one might be 1 or 2. So in this case, we have 1 outcome, I would say. And then in the second case, if the first die is like, is 2, the second could be one of these 2. So we have 2 outcomes. And if this is 3, so you could have 1, 2, or 3. So that is 3. And if this is 4, that will be 1, 2, 3, or 4. So that is 4. And if you just keep doing this, if the first one is 6, then second one could be 1, 2, 3, all the way to the 6. And that will be 6 outcomes. So in total, we should add these guys. So 1, 2, 3, 4, 5, all the way to the 6. So 1, 2, 3, 4, 5, 6. You can add them. So 6, 4 is 10, 15, 18, 20, 21. You may do this, but there is something we call Gauss formula. It's better to use as well. So when you are adding the integers from 1 all the way to some number, in this case 6, you are taking the last number, which is 6, and multiplying that number by 1 more of this, which is going to be 7, and divided by 2. which is 21. So that is called Gauss formula. So another way to look at this, like 6 plus 1 is 7. And then 5 plus 2 is 7. 3 plus 4 is 7. So if you pair the first and the last number, that will be 7. If you pair the second and the second from last, that's also 7. So since you have 6 numbers in our list, that will be 3 pairs. Each pair is add up to 7. So 3, 7 is 21. That's something you can go with as well. But the Gauss looks like this: 1, 2, 3, all the way to the end. You just take the last number and multiply this by one more of that number, divide by 2. And then this is called Gauss formula. Okay, Gauss formula. It's good to know because if you have like numbers start from 1 all the way to the 1,000, you don't want to like add them one by one. So you can just use the Gauss one, or you can just use the pairing idea, but either one is okay. So the question was asking the probability. So the desired outcome is 21. The total outcome is 36. So if you do this, 21 out of 36. So both divisible by 3, which is 7 over 12. I think that's the choice. So since we don't have too many outcomes, so we can kind of list them. But as you see, as soon as you organize your counting, so you don't really need to list everything. So you know what's gonna be next and stuff. So you can see 1, 2, 3, all the way to 6 is coming out. So you can go from there just without listing. Okay, so that would be the answer. Say be extra careful while you are dealing with counting questions. Like if you remember the previous problem, it was a probability problem. So if you miss one of them, your answer will be different. So if you are dealing with the counting questions, so extra cautious is good. And if you look at the choices as well, they are really close to each other. So if you are not careful enough, then you might miss one, or you may count something twice. So be careful with that. This is possible. So like there are a couple of ways you can approach to these kind of problems. The first, maybe the most important one, just be slow. Try not to be quick when you are counting stuff, because you don't want to miss any, and then you don't want to count stuff twice. Okay, so that is important. And the second, organize your counting. Okay, so how do we do that? Depends on the question. There are different ways to approach it, but here's what I'm going to do. I'm going to count the rectangles that is combined with some other ones. Like let's say we have only one section rectangles. Let's see one section ones. One section rectangles. So what does that mean? One section means like, you know, I can take this guy. This is one, just itself. And then this is like another one that is also just itself. And then this is another one that is also just itself. So if you just consider only one section, you can have 3 of those, right? So let me write that 3 with one section. And maybe we can have some rectangles that has 2 sections. Okay, so which one are those? Like we have this guy, maybe if actually, maybe I should count this as well. Actually, I did the other way around. So I just count the largest one, and then this largest and this largest one. Maybe I should have done the other way around. So I can say 2 sections or 3 sections, but I will go this a bit careful, because when I say one section, I actually meant for the rectangles that is combined with only one of them. But I think when I say section, that should be a little bit differently. So I will just take this guy as one section, and I will take this guy as one section, and then this guy will be one section. So other than like this guy, and this guy, there is no other one rectangle that is only one section, one piece, one region. So that is why I will take those 3 instead of the largest 3 separately. Okay. When I say 2 sections, I will say you know, this is a rectangle with two sections. This is one, this is two. And your goal is to see another one that has only two sections. Maybe you can see like these two, right? Now you can see these two. That will be two sections as well. But do we have anything other than those two? We have one right here, and then one right here, and one right here with two sections. And other than that, maybe we can see this is and this one. Like if we combine these two, like this guy is also another one. So you can kind of see that's also another section one. And with the two sections, we have already how many? This is one, this is two, this is three, and this is four. And I think we have one with like that. So let me see if I miss. Yeah, we can take maybe this guy. That will be 5 of them. And if I go with 3 section, okay, so I can just try to combine 3 regions. So let's see how many of those we have. So we can have like this whole thing, right? Because this is like 1, this is 2, this is 3. And actually this is like this is the one that we didn't count it. And then this is the one, another one we didn't count it. And then this largest one, another one, which looks like we have 3. If you add them, you got 11. So D looks like 11. But this is kind of a bit tedious or a bit challenging to look at it. So you can try just counting carefully. So you can kind of split them into regions. So like you can just say, how many rectangles are there that is combined by only one rectangle? How many rectangles are there that is combined by only 2 rectangles and stuff like that? So you can do some counting similarly that way, but if you do so, they will get the 11 as well. So let's try one more time. So my question is the number of rectangles that is combined by one rectangle. Okay. So let's take a look at that way. So this is the smaller one is 1. This is another one, that's 2. That's just one rectangle. And this guy, the 3, and then this larger one is 4, and this larger one is 5. So we have 5 rectangles that is itself is a single rectangle, okay? But if you have some rectangles that is combined with 2, okay, so let's see which ones are combined with 2. We can say this is like one rectangle, this is 2, but when I say the largest one, I already count that, so we don't want to count again. But you know, this smaller one and this smaller one, if you combine these two, that will be a rectangle, so which I didn't count it. So that's combined of 2. And do we have another one right here. So if you look at this one and then this one, so this guy right, let me kind of show that. So this is also combined of 2 rectangles. So far we have this guy and then we have this guy. So we have 2 rectangles that is combined with 2 rectangles. But other than those, do we have any? So like I can't counted the larger ones, which I don't want to count again. So we have 2 so far, if I'm not mistaken, if I'm not missing any. So that is 2. If I find something, I will add it. And then combine with 3 rectangles. So if you look at this is 1, this is 2, this is 3, but those 3 will not make a rectangle. And actually with 2, we have one more. So, you know, this is also another one. If you look at this one, so this is a smaller one, and then the other one inside. So that means this is also another one. So that has to be 3 actually. If I see another one, I will say as well, but so far we got 3. That is combined with 2 rectangles. With the 3 rectangles, let's see if we have any. So we have this guy and this guy, is 2, which doesn't look like that. So which is, we are gonna find 3 rectangles that is combined. It doesn't look like we have so far that much. But if I do with the other ones, let's see how many we have. So we have already 8, right? So for sure it's 8. But how many do we have more that we didn't count it? With the 2 rectangles or 3 rectangles? Maybe we can try 4 rectangles. That would be okay as well. So if you look at the, like this guy, we count that as 2 rectangles. Do you see any that I'm missing right now? I feel like this approach doesn't really help much because in the previous one we got 11. So now it's 8. And I'm not sure if I'm missing something. Do you see any that I am missing? Before I testing. Okay.
You disable drawing.
Okay, so let me put it back. Do you see another one that I miss? Yeah, go ahead and try and show me. I list that in the first 5 because I said only one rectangle, which is one was this, one was this, one was that, and then one was this, one was this, and one. So when I take a rectangle that is just one, I count that already in my first 5. But my question is, do we see any rectangle that's combined with 2s or 3s or 4 rectangles that I didn't count it so far? So that is kind of what I'm trying to see. Yeah, I think we did this one as 2, we did this one as 2, we did this one as 2. And maybe with 1, I think I count this one as 1, 2, 3, 4, 5. Actually, this is not 5, this is more than 5. So if I want to take only one rectangle, you know, I have this one, 1, this one is 2, this is 3, this is 4, this is 5, this is 6, then this is 7. So we already have 7 right there. So let me see if I'm missing any other one. So let me show you again. This one is 1. This is 2. This is 3. This is 4. And then this is 5, like this. And then this is 6, right? And then we got those, just the one that itself. And then I guess this is 7. So we already have 10 already. Okay, at least we have 10. So in our previous approach, we had 11. So I'm not sure which one I'm missing now. So this is 1, this is 2, 3, 4, 5. Okay, yeah, I think there is right here 6, like this. Okay, and then we have this. And then we have these 2 or these 2 together, or these 2 and these 2. Yeah, I think we have, this is gonna be 8 then. So if you do so, that will be 11. So it's the casework is not really, so in this case, yeah, it's 11. So I just did 11 in our first approach anyway, but I was trying to do it slightly differently. So whenever you are a bit careful, so you actually get that 11 as well. The answer was 11. So in one of the previous problems, we had a right triangle, right? So, and then if you remember, we had some Pythagorean triples that I mentioned, and I'm trying to remind those because whenever you have some figures like trapezoid or some other like 4D shapes, I mean, 4-sided shapes, 5-sided shapes, any polygon, it is better to make a triangle, especially right triangle, because we could have more idea about those. So since we are told this is 12 as altitude, we are told the altitude. This altitude is the distance between AB and DC. And then when you have trapezoid, AB and DC is parallel. So any point, like when you take the distance between AB and DC at any point, it has to be 12. So if I want to drag that 12 to this side, this is also 12. And if I drag this to this side, that will be also 12. Okay, so this is 90 degrees. And this is also. So this is 12. And this is 12. So at this point, you may use the Pythagorean, which is okay. But instead of using Pythagorean, I like to use the Pythagorean triple because Pythagorean triple will make our life way better. So the first Pythagorean triple that we use is 3, 4, 5. So if you have any multiple of these three numbers in a triangle, in a right triangle, that is also will be fine. So if you look at the 15, like the hypotenuse, the largest side, so 5 times 3 is 15. If you multiply these numbers by 3, you got 12 and 9. So 12 is right there. So which means these two are multiple of 3. 3, 4, and 3, 5. That means this guy, this piece right here, has to be 3 times 3, which is 9. And if you don't see that, you can use the Pythagorean. You can say square of this guy equals square of 12. Square of this guy plus square of 12 equals 15 squared. And you can get that 9 as well. And the same idea, this is 5 times like 4. This is 4 times 3. But yeah, this is 4 times 5. This is 4 times 3. Okay, 4 times 3, meaning that these two sides are multiplied by 4, because if you look at the 3, 4, 5, that means the other side should be multiplied by 4 as well to get 16. So this side is 16, this is 12, this is 20 by Pythagorean triple. And again, if you don't see that, just use the Pythagorean theorem itself. And AB is 50, which means this piece is also 50. So the rest is just finding the area. And then you can do this 2 ways. The first, you may find the area of the right triangle right here, which is like this leg times this leg over 2. And then you can add area of the rectangle. Okay, so that will be like 12 times 50. And then you can add area of this triangle, which would be like 12 times 16 over 2, because 12 is this side, 16 is this side, the legs are multiplied. And 9, I can cancel 6 and 2, which is gonna be just 6 times 9, which is 54. And then second one, if you multiply 5 by 12, which is 60, so that means this is gonna be 600. And the last one, if you divide, I don't know, maybe 16 by 2, which is 8. 8 times 12 is 96. If you add 90 by 50, which is 140, and 6 by 4 is 10, which is 150. If you add 150 to the 600, so that looks like 750. And that's the answer. Yeah, I think this is like good to do that. But there is something we probably need to know as well, which is called area formula for a trapezoid. So that is like this. The area of the trapezoid is the sum of the bases. I'm gonna call base like maybe base times base, and divided by 2 times height. And then in this case, base is gonna be called this AB and DC. So if you use that, so that is 50. And then this was 16, that's 9, that's 25. If you add 50, you got 75. And then divide this by 2 times height is 12. So if you cancel 12 by 2, which is gonna be 6. And if you combine these, 125 times 6. So if you do so, you will get 750 as well, okay? So again, this is just the area formula for trapezoid. Sometimes it's good to use this one instead of just doing separately, but either way is good.